All right, so I'm going to be doing a second unit on functions. In this unit, what I'm really going to be focusing on is inverse functions and compositions of functions. But before we get into any of that, I want to do a quick recap on some things. I want to discuss the definition of a function, zeros, and interval and set notation. In the previous unit, I consistently used interval notation. However, we also have something called set notation that I want to describe in this video. To begin with, the definition of a function is a relationship in which each input has exactly one output. Okay, it has to have exactly one output. All right, so for every input, there's an assigned output. If an input has multiple outputs to it, that causes it to fail to be a function. For example 1, we have a few cases of relationships. But are these relationships functions? Okay, take the first, which is a mapping. It shows us how the inputs go to outputs. Okay, -3 goes to 2, -1 goes to 3, both 2 and 4 go to -4. Okay, the only odd kind of thing that's happening here is in that last part where 2 and 4 both have an output of -4. But that's okay, because every input, each of these inputs, if we were to ask a person what will be the output for that input, there is one answer that we get. Okay, so if we asked, what is the output for a 2, you would be able to respond with -4, confidently. And if we asked, what is the output for 4, you could say -4 as well, and be confident that that is correct. All right, so that is a function. The second is a graph of a relationship. Okay, and we still want to go by the definition, every input should have exactly one output. But for graphs, we have a physical test that we can use, which is called the vertical line test. Okay, so I'm going to take this paper, and I'm going to move it along this direction, watching the edge that's here. If the graph contacts the edge of this paper more than once, at any point, it fails to be a function. Okay, so as I move over right here to that vertex, everything is good. Okay, for an input of a 0, I get an output of a 0. But as soon as I move past that, say I'm at 1, I get multiple outputs. I have an output at -1, and I have an output at 1. In that spot, it fails to be a function. Okay, and it'll continue to fail to be a function forever to the right. So this will be no. For the third, what we're looking at is a select set of coordinates. In a way, this isn't much different than what we have here. You could imagine a 2 in the input bubble going to a 3 in the output bubble. Okay, and a 3 goes to a 0, and a 4 goes to 1, and a 3 goes to 3. So really what you want to look at here is, do we have any duplicate values in the inputs or the domain? Okay, so I'm going to look at the 2, the 3, the 4, and the 3. And as I read those, you should hear that the 3 gets mentioned twice. Okay, so 2 goes to 3, said and done. 4 goes to 1, said and done. 3 sometimes goes to 0, and 3 sometimes goes to 3. Okay, that causes it to fail to be a function. Next, I'd like to talk about a 0. Okay, and if I have not described a 0 specifically before, it is essentially the same thing as an x-intercept. It is the exact same thing as an x-intercept, also sometimes referred to as a root. Okay, a 0 is an input value such that the output is 0. So think about that as an x-intercept. It would be a value for x, an input such that the output is 0, so then it just stays on the x-axis. Algebraically, you can solve for these zeros or these x-intercepts or these roots if you take your function and you set it equal to 0. Okay, so consider these two functions. F of x is equal to 5x minus 17 and g of x. Okay, in f of x, what we're going to do is just replace f of x with 0. We're going to set it equal to 0 and simply solve it. Okay, we're going to add the 17 to the other side. That's going to equal 5x. You then divide by 5. And that's it. It's an unusual looking number, but that is it. That will be the 0. That is the number that when you plug it in here, the whole thing becomes 0. You can evaluate that as a decimal if you want. 17 divided by 5 is 3.4. Okay, so you could also describe the 0 as 3.4. Both are acceptable. The point is that they're both numbers that when plugged in for the x, the whole thing becomes a 0. Hence, it's called a 0. All right, g of x is a quadratic. It's a quadratic. And what that means is it can potentially have 2 zeros. Okay, our standard approach for anything that would be a polynomial, which would include quadratics, is to factor. And if it can factor, you can identify those zeros fairly quickly. Okay, so let's think about this one. We'll set it equal to 0. We're going to look for two numbers that multiply to give us negative 21. Okay, so we're probably already thinking about 3 and 7. They need to multiply to give negative 21. That means that if these are the numbers, one of them is negative. Okay, and when you add them together, you should get positive 4. Okay, so that will be the right set of numbers. You're going to want a positive 7 and a negative 3. That way when they add together, you actually get a difference of positive 4. Okay, so we're going to get x minus 3 and x plus 7. And now that it's in factored form, if we can make this factor equal to 0, the whole thing becomes 0. Okay, and that would be a 3 that you could plug in. That would create 0. This would create a 10 with the 3, but it doesn't matter because that 0 times 10 is going to give you 0. Likewise, here you could plug in a negative 7, and the whole thing becomes 0. All right, so our answers are going to be those two. You actually have two zeros. You have two x-intercepts. All right, for examples 3, 4, and 5, we're going to be looking at set notation and interval notation. We're going to start off with some inequality. This one says that negative 2 is less than x is less than or equal to 3. And what I'm going to do is make a graph of that on a number line. Okay, now the key numbers that I need to identify are going to be negative 2 and 3. Okay, so I'm just going to choose this to be 0. Just give a location for that. And if that is 0, then 3 is going to be over here, and negative 2 will be there. So x is going to be all the numbers that sit between these two values. It is going to include 3, but not negative 2. We actually have an open interval over there. Okay, so at negative 2, we're going to have an open circle. At 3, you're going to have a closed circle. And then what we're going to do is connect those two together to show that any value that's in here will be part of the set. All right, so let's talk about interval notation first, because we've already looked at that a lot. Okay, we have values that go from negative 2 to 3, but it's going to be open at negative 2. Okay, so in interval notation, you're going to have parentheses, negative 2 for the open interval, to 3, closed bracket. And that's it. And to be honest, if you get used to this notation, this will be preferred over set notation. All right, for set notation, you're going to use braces. Okay, you're going to start with braces. You're then going to identify your variable, which is x. You're going to draw a long line like that. And so far, what this reads as, it's the set of x's such that, you can read that as such that. It is the set of x's such that, and then afterwards, you describe what that set would be, which in this case is right here. It is the set of all x's such that negative 2 is less than x is less than or equal to 3. And that's it. All right, now that may seem really simple to create because all you had to do was copy that into this spot. However, if you are given just a picture like this, or maybe you have a picture of a graph, you do need to build the inequalities that would go with it. So it isn't as simple as just to take something and then write it into that spot. You're usually going to be looking at some diagram, then from there, making a decision about what the inequality would look like. For example 4, we're going to be graphing x is greater than or equal to 5. Okay, so for this graph, I don't even need to identify a 0. I can just simply put a 5 anywhere because that'll be the only number that I need. Okay, now x can be 5 because it has that equal to part. So you can have a closed circle there. X can also be anything that is greater than 5, which is going to be in that direction. Okay, so what I'm going to do is I'm going to start to draw a line that direction. And at some point, just put an arrowhead to indicate that it continues to move in that direction. Okay, set notation. It's going to be the set of x's such that x is greater than or equal to 5. Interval notation, we have a lowest value of 5, and it can be 5, so it's going to be a bracket with 5, and it goes on to infinity, which for infinity, you use an open interval because it is not a defined endpoint. Okay, for example 5, we get two different parts here. Okay, we got x is less than or equal to 6. We also have x is greater than or equal to 7. And if you think about that, in a way they kind of contradict each other. It's going to be anything less than 6. Let's say that 6 is here. It's going to be anything that direction and including 6. Then 7 and anything in that direction, the greater than. Okay, so we don't actually have this closed in area. It actually spreads out to the sides. We do have closed circles here. We're going to indicate that it continues in that direction and that direction. Okay, and again for set notation, because you've already got the inequalities, you can just copy that information. For interval notation, what we're going to get are two intervals because it's like we have a break between our numbers here. Okay, we're going to come from negative infinity up to 6 with a bracket because it is included. We'll pick up again at 7, included, so bracket, and go to infinity. And for example 6, we are going to state the domain and the range of these graphs. We're going to do them in set notation or interval notation. You might not necessarily want to use one of those, so you actually get a choice of set notation or interval. However, we're going to go ahead and start with this graph here, which in a sense might look a little bit weird compared to that because it has these open circles and then these other dots. The way that we can state this one, you can actually do it in set and interval notation. So what I'm going to do is actually show you both of them. Okay, so let's talk about the domain. The domain is all the x's we're allowed to put in there. It definitely starts at -2. It definitely finishes at, let's see, 1, 2, 3, 4, 5, 6. Okay, -2 to 6. All right, so let's take a look at these weird spots here. You do have a break here. We do have discontinuity. However, as you're looking at the x values, you do have an answer for that spot. It just happens to be located somewhere else. It's that removable discontinuity with that extra point just offset. Okay, same thing happens over here. We have discontinuity, but we do actually have a value for what would be x equals 5, which means that we do have x's for the entire domain of -2 to 6. Okay, so your domain in interval notation is going to be a bracket at -2 and a bracket at 6. The set notation version of that, we'll just state it underneath, you're going to use braces. It's going to be the x's such that, and we're going to build an inequality here. Okay, lower bound is -2. That would be less than or equal to x, which will be less than or equal to 6. All right, the range. All right, thinking from bottom to top, the lowest point that we have is here, which is going to be at -1, and that's included. The highest point that we have is going to be here at, let's see, 1, 2, 3. It's going to be at a 3, but that would be open. That would be open. Okay, and now as you look in between here and there, and you scan across, there's always going to be some value there. Okay, we don't have any breaks in the range. There's a hole here, but look, there's values there, 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 and there. Okay, so the range is going to have a single interval that starts at -1 and goes up to 3, except open at 3. In set notation, this will be the y values such that it starts at a lower bound of -1, less than or equal to y, and goes up to 3, but does not include 3. Okay, no equal to. All right, so let's go back to the first graph, which might appear to be a little bit more simple than what we have for the second one, because all it is 4 points. Okay, but if we start thinking about interval notation for this, for interval notation, you've got breaks all over the place. You got breaks in the domain, you got breaks in the range as well. Okay, if you ever have a graph that is actually just discrete points, just individual coordinates that we have here, the best approach is going to be set notation. It's going to be set notation. And all you have to do is this. You're going to say that this is the domain, you're going to use braces, and simply list all the x's that would be there. Okay? So we have an x of a 0, we've got a 2. Let's count these out. 1, 2, 3. We got 4 and then 6. And that's it. And you don't want to use interval notation. There's no practical reason to do that. The range is simply going to be all the y values. So you've got 0 that starts here, then it goes up to 1, to 2, and to 3.
Wait, there was.